In this lecture we will discuss about DFT and how it is related to LTI system output. So first we will discuss about the circular convolution. Already we have seen in the last video that how circular convolution of two sequences can be computed through a linear transformation process. So now here we will see how the circular convolution is related to linear convolution, so that we can map that the map between circular convolution and the LTI system output. And we will talk about few examples where we will explain that how it is related to LTI system output through linear convolution. So as we know, basically LTI system, that is a linear time invariant systems, and this is a discrete domain where xn is the discrete time signal at the input of finite length of capital N. H of n is the impulse response of the LTI systems of finite length also of length sequence capital M. Yn is the system output which computed through a linear convolution process, where the output sequence length capital N is equals to the sequence addition of the sequence length of both the inputs of the linear convolutions minus 1. So if input signals length is 4, impulse response signal length is 3, so the output signal length would be 4 plus 3 minus 1, that is 6. Now this is the property of DTFT, that is discrete time Fourier transform, that the convolution property of discrete time Fourier transform says that if we have a relation in time domain yn equals to xn convolution h of n, if we take the DTFT of both the sides, it would produce an equation which is something like that the spectrum of both the inputs to the linear convolutions get multiplied to produce the spectrum of the output signal, where h of omega is coming from DTFT of h of n, and so this is called frequency response of the system, where x of omega is the spectrum of the input discrete time signal and y of omega is the spectrum of the output discrete time signal. So if we just try to consider one specific example, let assume that this is the spectrum of our input signal, where we extended the signal spectrum from 0 to pi, because this signal is basically 1/4 of the full period, and so we know that due to the periodicity property and for real signals the event symmetric property, so this is sufficient enough to draw this interval for extending the rest of the portions. So where omega equals to pi corresponds to linear scale frequency half of sampling frequency fs by 2, and this is the discrete time system frequency response. So after multiplications, if we multiply these two functions in frequency domain, it would produce something like that. This is an arbitrary examples, and so we are also extending output from 0 to pi, and rest of the sections we can extrapolate. Now this is the same thing as actually we discussed about DTFT. The problem is that we can't store these particular signals in computers, so that's why the process is to sample. So if we sample this particular expression, means if we are sampling the left hand side and we are also sampling the right hand side, so if we do sample to the left hand side, individual spectrums are sampled by some finite number of sample points, which are basically shown in the dotted lines, and so same interval. So after so how do I do these multiplications? So each sample to sample will get multiplied to produce the corresponding sample output at the yk. So what is the relation between these two? We are basically sampling these expressions over omega, and that's why we are producing these things. So what is this? This is nothing but DFT equation of system input output, where yk is the DFT of the system output, hk is the DFT of the system impulse response, xk is basically DFT of the input signal. So now if we consider ns equals to even, generally we consider the number of points during the sampling in the frequency domain. These are taken to be even numbers. So this sequence length should be even, as because this is even number, even by 2, that is also integer number plus 1. So if we just try to explain why this is plus 1, let me explain this. Let's say this is the frequency axis f, regular Hertz frequency axis, and over which this is the sampling frequency fs, this is the 0 frequencies. Let's say capital ns we are considering as a 6, so that means if we just pick up these points 0, 1, 2, 3, 4, 5, let's say this is 6. So 1, 2, 3, 4, 5, 6. Sorry, this is not a point. This is not a point. Actually, this is not a point. So this is 0, 1, 2, 3, 4, 5, 6. That means this is 7th point. So now 6 point means up to this particular point. This is 6 point. So now if we just do this calculation, ns equals to 6. 6 by 2 equals to 3 plus 1, 4. That means we are taking this point 2, 3, 4. So now if it is sampling fs, so this point is basically fs by 2. So how many number of samples we are considering to cover the whole, cover this one half of the sampling interval, that is up to fs by 2. That is a 4 number of sample point. So for even number of samples, we are basically taking this equation ns by 2 plus 1. Now if we just talk about LTI system output and circular convolution, how this can be related, let's take a look. This was LTI systems linear convolutions. We took the DTFT, we found the DTFT expressions, we sampled these expressions to have a discrete or quantized spectrum, that is a DFT relation between input output. Now here from this DFT to this particular steps is basically the circular convolution property of DFT. This is one of the property of DFT. So if you take the inverse DFT, it would be equals to exactly that circular convolution between these two sequences in time domain. Now under the condition that if ns, number of sample points during spectral domain sampling, if it is greater than or equals to capital N equals to actual signal length after linear convolution, then it is this yn is basically equivalent to this particular yn what we already achieved through linear convolution. So under the condition, the circular convolution output is exactly equals to the linear convolution output. So the system output, LTI system output, we can compute through linear convolution or through circular convolution. So this is basically the relation. The condition is that. Now linear and circular convolutions, so how we can correlate to each other, how we can map to one convolution to another convolution. Let's take a look. That we have L sequence length, M sequence length, these two might be different, and we have finally output as a N sequence length. So obviously capital L should be less than capital N, as well as capital M is less than capital N, because all these things are sequence numbers, so all them are positive integers. Now under the conditions, we have seen in the previous slide that circular convolution can be related to linear convolution. That is the same answer of linear convolution we can achieve through circular convolution under a specific condition when the length of both the sequence will be same, and that length should be exactly equals to the output length through linear convolutions. So what do we do basically, since L is less than N, so there is an opportunity to achieve the same length sequence for both of them, similar for N is less than equals to N. So that's why what do you do basically, we will append zeros at the end of the sequence, that is called zero padding. Already we have seen what is the technique called zero padding. So if we do zero padding, so L can achieve now to equals to capital N. So that means we have originally sequence length is less than capital N. Now after appending zeros at the end, we are making the sequence length same exactly as the length of linear convolution output. Similarly, through zero padding, we can make it full N length sequence for impulse response as well. Then we will do circular convolution that will exactly produce the same answer yn what we already achieved through linear convolution. So here all the sequence length are same. Here they might be different, so it would be also different. Let's see one example. This is an example of linear convolution. Already you know how to perform it. LTI systems where input sequence is x of n, h of n is given, so we can compute y of n through this particular matrix form y. it is basically a simple process that we are considering one of the signal as a row index, another signal as a column index, and we are placing the samples of these particular signals on the top of the rows and columns. Then we are filling up the cell matrix cell values, just multiplying the row and column index values, row and column values. And then y of 0 is basically the numbers comes on the top of the strip, y of 1 basically comes on the top of the strips. In that way we can compute, that is the output. So this is the linear convolution output. So if we just check this output, that is just sum it over the diagonal strips, you will come out with the result. Now example 2, we would achieve the same answer through circular convolution. How is it possible? The capital L value, the sequence length equals to 1, 2, 3, 4. So input signal length is 4, impulse response signal length is m equals to 3. So if we just do linear convolution, we found the answer is that. So now this is the process. Here we will solve through circular convolution. What do we do? Basically we will zero pad. How many number of zero should I pad? Before that you have to calculate what is the expected number of sample output through this linear convolution. So 4 plus 3 minus 1, that is 6 is the output length. So we have 4 number of samples. So 6 minus 4, 2 number of 0 we have to append at last of the signal sequence. So what to do? Basically after 0 padding, 2 sample points we will add, that is finally it would achieve n equals to 6. So we have this xn sequence, it's a column vector 6 by 1. Similarly h of n, originally there are 3 sample points, so we will add another 3 sample points to make it a complete length of 6. So after that it will be a complete 6 sample point sequence length. Now already we have seen during circular convolution presentation that the second sequence we can consider through a matrix form, something like that, and after that this particular vector is, once it is being taken at the end of the matrix, and if you multiply these two matrix with a vector, that would produce a vector, because this is 6 by 6 and this is 6 by 1, so output would be 6 by 1. So if you multiply these two matrices, you will get the output exactly these things. So that verifies that the circular convolution can produce the same answer of linear convolution with a specific constraint, and constraint is that both the input sequence length should be same as the linear convolution output sequence length. Now this is the interesting point. Suppose the same problem we are trying to solve, just our target is that output sequence length should be 8. That is, the target is n is more than 6. We can take this one as a 7, this one as a 8, this kind of a 1000 number of sample point as well. That would be true for all. So now if we try to solve it, just logically try to understand what happened exactly. Our output sequence length, we want to make it as a 8 number of sample points of LTI system output, but originally it would produce valid answer 6 sample points. So another 2 sample point we have to append zeros. So that exactly we would achieve through circular convolution. Let's see how it is possible. So we are doing 0 padding, so it should have to equals to capital 8 capital N. So after that we have to append 4 zeros, so we append 4 zeros here. So it is now total L equals to capital 8, and this is 3, so we have to append 5 zeros at the end, so that finally it would be of 8 number of samples. So after that, if we just do circular convolution, just take the same process what we exactly mentioned here, and it would produce exactly the same valid output. First 6 samples and last 2 samples would be 0, what exactly we expected, because the valid answer is 6. So there is no way to get another 2 sample points, valid sample points. So only way is that you have to append 0, as if this particular output you are passing through a 0 padding operations of additional 2 zeros at the end. So this is the logic. So that's it. So now in the next topic we will discuss about filtering of the long data sequence. There are 2 different algorithms.